Well, thank you very much. Thank you very much indeed. And good morning, ladies and gentlemen. I'm talking to you from Melbourne in Australia, where it's very early on Friday morning. And I'm very honoured to give this lecture named after a man who I had the great pleasure of knowing and with whom I had several discussions on a mutually favourite subject of ours, deep foundations. George Osterberg was a notable foundation engineer and a prominent innovator whose development of the testing technique named after him, the Osterberg cell, has been a game changer in pile load testing, especially for tall buildings and heavy structures. So the subject of my lecture today is a topic which George had a great interest in and one that I've focused on over the past 30 years or so, and that is the design of foundations for tall buildings. In this lecture, what I'd like to do is to outline my thoughts on the design process and steps that can be taken to try and reduce the risks involved in the design and subsequent construction of tall towers. I want to start off just by talking about the design process generally for high-rise building foundations, and then outline some of the risks that I see associated with those foundations, some of the problems and solutions that we can contemplate. And then I'll talk relatively briefly about three examples, the Burj Khalifa, the Dubai Creek Tower, and the Millennium Tower in San Francisco. I think we're all aware of the fact that over the past 2 decades or so, there's been a dramatic increase in the number of tall buildings completed, and with the occasional little dip, but we see that typically now there's something of the order of 100 to 150 tall buildings completed every year. So these are major structures, and they involve major challenges in the design of foundations for them. And some of these challenges include having, of course, high vertical loads that increase non-linearly with height, because as the structure gets taller, it needs to be more robust and heavier. And so we have that as a prime issue. We also very frequently have low-rise podium areas adjacent to the tall tower, and so we have a potential for differential settlements. Clearly, we have high lateral forces and moments from wind loading, and that's of cyclic nature. And we also have seismic forces on the foundations that we have to design for, which give rise to both inertial and kinematic effects. And then in terms of human comfort, we have to look at the dynamic response issues of the structure foundation system. Now, some of the ingredients for economic foundations, as I see them, firstly, you have to have the right sort of concept. Then you have to have appropriate design criteria and methods, appropriate ground data and design parameters, quality construction, and appropriate foundation element pile testing. And I've highlighted that because, of course, this is where George Osterberg has made such a notable contribution. And then ideally, we need to have performance monitoring so that we can track whether or not our design expectations are being met. Just very quickly, of course, I think we all recognize that the three key options that we have for foundations are the raft or mat foundation, the piled foundation, and a combination of the two, the piled raft foundation, where much of the load is carried initially by the piles, but the raft actually provides an additional source of resistance and stiffness. The design issues then that we have to cater for are firstly ultimate capacity, then settlement and differential settlement and tilt of the tower, the response of the foundation to lateral loads and moments, the dynamic behaviour of the foundation, the earthquake response, These are all geotechnical issues that we as foundation designers have to deal with. And then, of course, we associate with our structural colleagues to look at the structural strength of foundation elements and durability. We, in our practice, have a three-stage process of design. A preliminary stage where we just try and develop the concept for the foundation system, and we use relatively simple approaches to do that. Then we have a detailed stage where we develop and optimize the design, interact with our structural colleagues, and that involves generally the bulk of work. We then have a final stage where we finalize the design and the parameters. We check with alternative analyses, and also importantly, we have a peer review. If not at that stage, then preferably actually right the way through. And I've listed here that the design tool should be consistent with the stage of design, so that obviously you don't try and use three-dimensional finite element methods in a preliminary stage, but you use a fairly simple approach. And whatever the stage is, any complex analyses that we do need to be checked with simpler methods, because quite often with contemporary software, we are not always in control. The design analyses that we do, ultimate limit state, which involve looking at the overall stability and the geotechnical capacity of the foundation. And we also look at cyclic loading and try and limit that to reduce the risk of getting degradation of shaft friction. And so we try and limit the cyclic loading component of the loads to no more than 50% of the shaft friction capacity. Then we have to look at what we call serviceability here, limiting the settlements and angular rotations. And with tall buildings, we tend to be a little more lenient, perhaps because we have to, because of the large load. So typically our maximum settlement target would be no more than 100 millimeters and an angular distortion of the order of 1 in 500 or better. With respect to dynamic loading, that's an important issue, not only because of human comfort, because the foundation natural frequency and the damping also affect the structural response and actually the wind loading. And with respect to earthquake loading, as I mentioned before, we have to look at two components. One is the inertial loads that the structure imposes on the foundation, and the other is kinematic loading, which is induced into the foundation system because the ground moves during a seismic event. The key parameters that we need to assess are the ultimate shaft friction, the ultimate end bearing, the soil stiffness or modulus for vertical loading. And again, we have to recognize that we have different modulus values for long-term loading, which generally involves dead plus live loading, so sustained loading, and short-term modulus values where we have wind and seismic loading. And because of that short-term nature, the stiffness of the ground in that circumstance tends to be greater than for the long term. Then in terms of lateral response, we need to estimate ultimate lateral pressure and the soil stiffness and modulus for lateral loading. And finally, the dynamic soil stiffness and damping. In terms of soil structure interaction issues, when we do our analysis for geotechnical resistances, we factor down the capacity, the shaft and end-bearing capacities, but we don't factor down the pile capacities when we're doing structural checks, because that would artificially limit the load that could be induced into the pile itself. In terms of the superstructure stiffness, that will affect the settlement and will be beneficial to the differential settlement, and that's best taken into account in the structural analysis, as I'll mention in the next slide. And just a note about the pile load distribution, I've just got a warning here that some programs that we may use have an assumption that the raft itself or the mat is rigid. And for a very large building, such as we have with tall towers, that can lead to serious overestimation of the pile loads near outer edges. And so we really do need to account for the actual raft flexibility. It's important that we have a good relationship and cooperation between geotechnical and structural designers. That, I believe, is essential for a successful outcome. And what we do as geotechnical designers, and a key output of our work, is to provide values of the pile stiffness, that's axial, lateral, and rotational stiffness, for each pile within the group. And these stiffnesses take into account interaction effects through the soil. And those then are used by our structural designers to take account of the superstructure stiffness. So they put our stiffness values into the structural model and get more appropriate values of settlement and differential settlement. Now, some of the risk factors involved here are fairly obvious. If we have inappropriate design parameters or we use an inappropriate design approach, that can be a risk. Inadequate investigation can be a risk because if we try and economize on that, we may finish up with an inappropriate ground model. And then we have what I call geotechnical imperfections, and I'll show some of these in a moment. But typically, for example, soft layers below the piles or sloping bedrock or uneven layer thicknesses or the presence of boulders. And then, of course, risk factors are present very clearly in terms of construction deficiencies and imperfections in the construction process. Now, some of the measures that I think we can take to reduce those risks, importantly, I think independent peer review of the ground investigation report needs to be done so that it makes sense not only to the people that did it, but also to people that review it independently. We then need to have an independent peer review of the foundation design, independent supervision of foundation construction, foundation element testing of the piles or the barrettes, and monitoring of the settlements during construction, because that will enable us to compare measured versus predicted performance. And if there is some discrepancy, particularly if we find that the settlements are greater than anticipated, then the sooner we can find that out and take measures to try and rectify the problem, the better. So I think we need to treat these measures as insurance investments and not, as some clients think, in terms of additional costs. So very briefly, just to try and illustrate some of those points, inadequate investigation, if we just try and economise on boreholes, as I've shown here, we may miss out on what might have been an old riverbed, and so the soil in between those boreholes may be thicker, but our limited investigation would imply a rather nicer sort of ground profile, but it can be quite inaccurate and lead to inaccurate predictions of foundation behaviour. There are a series of what I call geotechnical imperfections. Some of these I've shown here, where you've got a foundation that's founded in rock, but there may be clay seams below. This can be a little bit dangerous if we've got strata of variable thickness, because if you've got the situation that I illustrate here, then even under vertical loading, you will tend to get a horizontal movement towards the longer piles. And if we have a compressible stratum under the founding stratum, then that can lead to problems, and I'll try and illustrate that briefly towards the end of my talk. And then here's another example where we have, particularly if we've got a glacial deposit, we may have some of the piles resting on boulders that we think may be rock, but they, in effect, in this sort of circumstance, act as piles with an enlarged base, not as piles bearing on rock. Then in terms of construction imperfections, in design, I've indicated here, we assume a perfect homogeneous vertical element, but if the construction is not done correctly, then we get situations as illustrated here, where we very clearly do not have perfect homogeneous vertical elements. So how do we cope with the consequences of these imperfections? Well, in terms of investigation, we need to be careful that we don't actually cause additional disturbance and settlement by the process of investigation. And that means, for example, if we do SPT testing, it has to be done very carefully so that we don't disturb sand deposits, and we need to balance fluid pressures in drill holes or cores. In terms of design, if we have to correct settlements, there are two approaches, one that I call hard methods and the other one that I call soft methods, and I'll explain those in a moment. Then we need to design remedial or enhancement works, and we need to also be aware that we have to be careful of the load sharing between the old and new elements of the foundation system. Now, I mentioned hard methods, and these are methods really where you actually apply some sort of load or stress to the structure itself. For example, you might try anchor stressing so that you pull down the high side of the building that's not settling uniformly, or you put additional loading on the high side, or you try and cut the piles so that, again, you try and get the high side to settle a bit more, or you try and jet soil below the pile tips, which I think I wouldn't certainly recommend, but it has been floated. And you can try and jack the foundation on the low side to bring the low side up, but that unfortunately has its problems because Newton's law says that you have action and reaction, and if you have a soft underlying layer, then you may not be able to jack as you wish, and fracture grouting is also another possibility. The second class of methods of correction I called soft methods, and these involve or can involve soil extraction or dewatering or compensation grouting, or another process that is termed the removal of soil support, RSS. Now, soil extraction has actually been used for quite a number of years. I've got a couple of examples here of it. There was a grain terminal in Iran some years ago which tilted and non-uniformly. And what was done here was that a trench was dug, and then there was a horizontal saw put into the ground below this side, and a series of those sort of slices of soil were removed so that assisted in the high side settling more. And of course, the most famous example of soil extraction is the rectification or partial rectification of the Pisa Tower in Italy, where the final solution was the drilling of 43 angled holes and the extraction of soil below the high side. And that, I think many of you may be aware of that, was done now almost 20 years ago. It led to a correction of about 0.5 degree in the tilt, and that is estimated to have prolonged the building life by at least 300 years. The other method that I've mentioned here is the removal of soil support, or RSS, which involves actually drilling a series of holes outside the building on the high side. And by removing the soil, you tend to remove some of the lateral support, and that tends to promote a limited amount of settlement. And all of these methods, the soil extraction and this method, are amenable to the observational approach, because you can start off doing things and measuring the response and keep doing what you're doing until you get to the required endpoint. In terms of foundation enhancement works, we have the option of repairing the existing piles if we can get to them to enhance their capacity or stiffness. We can look at extension of the existing pile caps themselves so that you make them larger, or you can look at the addition of new piles to strengthen or stiffen the existing foundation. One of the issues that I will mention in the last example are the possible side effects of remedial construction. You have to be very careful here, because when you install piles, as I'm sure you all know, you inevitably cause some sort of ground movement. And even if you excavate the ground for a pile cap extension, you will cause ground movements. And what you're doing with a tall building, which is partially or fully constructed, is that you are disturbing the ground, which is in a highly stressed state because it's got a very large load on it. So the effects then that can be felt by the existing foundation are much more severe than they would be in a so-called greenfield situation. So let me now just describe a couple of what I call positive cases where there's been a fairly logical process of design and the outcomes have been thus fairly favourable. The Burj Dubai, as it was originally called, or the Burj Khalifa, looked like this from the architect's concept in the early part of the 21st century. The main challenges here were that it was to be, and still is, as we speak, the world's tallest building. We had issues here with the foundation capacity for piles in carbonate soils or rocks, because we were aware from previous experience that you may have less capacity than you might expect with a silica-based series of rocks or soils. And then there was also a concern about the cyclic loading of piles because, again, from previous experience, cyclic loading in these sorts of carbonate materials can lead to a degradation of shaft capacity. And then, as I mentioned earlier, we have the potential, of course, for differential settlements between the high-rise and low-rise parts of the structure. Now, this is what the site looked like in September 2003 when the ground investigation commenced. And it was a fairly significant ground investigation, as befits this type of project. There were 30 boreholes, lots of SPTs, lots of pressure meters, lots of piezometers, and importantly, quite a bit of geophysics and cross-hole tomography, which was done primarily for two purposes. One was to assess the uniformity of the site, and the other one was actually to get quantitative data on the shear wave velocity, and from that, initial shear modulus values for the various layers within the profile. And this is a simplified profile. Fortunately, what the geophysics told us was that the site was relatively uniform, so that the layers were essentially horizontal. And we had a series of layers of calcareous underlying basis with various names, which I won't bother going into. But it was essentially the ground conditions were soft rock with typical unconfined compressive strengths, and forgive me, I'm doing it in megapascals, somewhere between about 1 and 3 megapascals. So I think a megapascal is about 145 psi, so up to about 400 to 500 psi. Now, the initial pile design, and let me just clarify who did what here. The main foundation designer was the company that was originally Hyder Consulting, and they were in the UK. And we, Coffeys, were the geotechnical peer reviewers. And we actually worked very closely hand in hand. We didn't sort of peer review after the design was done. We had a peer review process which was actually step by step, working very closely with the designer. And that proved to be a very satisfactory basis for interaction and cooperation. The tower, as designed by Hyder, was 196 piles, 1.5 metre diameter and 47.5 metres long, typically. The podium, which was a very large area outside the tower, involved the use of 750 piles, 900 millimetre, that's about 3 foot diameter and 30 metres long. And the raft itself was 3.7 metres thick under the tower and somewhat less thick under the podium area. This is the tower layout, and you see it's this sort of 3 legs or 3 arms of the foundation system, and each of these was relatively symmetrical. Now, when Hyder did their analysis, they used various methods of calculation. They started off with fairly simple methods and then went to quite sophisticated methods. These are 2 of their results, one using the program Repute and then another one using a 3-dimensional finite element abacus. And they got reasonably comparable results in the 60s, early 70s millimeters. We did completely independent calculations using an axisymmetric FLAC program and then one of our in-house programs, and got very similar results to theirs, early 70s. And subsequently, I did a simple check representing the foundation system as an equivalent peer and got almost exactly the same answer, which is probably coincidental. But it's nice that in this whole series of different methods, and again, 2 different organizations doing their own thing, we got quite comparable results. There was a significant load test program carried out, 3 static compression tests on 1.5 metre diameter piles, looking at various toe levels, 35, 45 and 55 metres long, a static compression on a smaller diameter pile, but now using shaft grouting to see the extent to which the skin friction could be increased by shaft grouting, cyclic compression test to look at the effects of cyclic loading, and a static tension test, and also a lateral load test. And here is the setup, and this was I guess around 2005 or so. So you see it was still a top-down loading process, and the maximum load got up to about 6,000 tonnes. So a pretty large load for that type of loading system. The outcomes of that load test program were very positive. The 1.5 metre piles were loaded to twice the working load. The 900 millimetre, 0.9 metre piles were loaded to 3.5 times working load. None of the piles appeared to be approaching failure. The skin friction values were in excess of design assumptions. The shaft grouting was indeed effective, but was not necessary because we had enough shaft friction without actually shaft grouting, and we weren't able, in fact, to mobilise the full end bearing resistance when we got to the maximum capacity for loading settlement. The axial stiffness was greater than we predicted, cyclic loading had little effect, and the lateral stiffness was greater than predicted. So all of that was very positive because the load test showed, in fact, that we were likely to be on the conservative side. Now, measurements were taken of the settlements very frequently during the construction process, and these are the contours that were measured when the building was around about 80% completed, and that was in early February 2008. And you see, the good news is that you get a pretty symmetrical settlement profile so that you don't have any tilts. And interestingly, although the raft was quite thick, that's 3.7 metres or 11 feet or so, you still had quite significant differential settlements of the order of maybe 15 millimetres between the edges and the centre. So even though that appears to be a very thick raft, it still has some significant degree of flexibility. When we compared, measured and calculated time settlement predictions, here is the settlement on the horizontal axis. Sorry, here is the distance along wing C, one of the three wings. Here is the settlement. And these are measurements taken at different times during construction. And this was the one that I mentioned in February 2008. And the maximum settlement there was around 43 millimetres. This was the predicted final settlement, long-term settlement, which was in mid 70 millimetres maximum. The shape was not dissimilar, and I think we estimated that probably the most likely final settlement would be somewhere between 50 and 55 millimetres, and that was certainly within design tolerances. And just to keep that in perspective, the maximum settlement here, we're talking about 50 or so millimetres, 2 inches. The tower itself will actually compress and shorten by around 300 millimetres due to a combination of elastic compression, shrinkage and creep, so that the building will actually shorten a lot less than it will actually settle. And here are pictures of the construction process, early 2006, 2007, and the grand opening on the 4th of January 2010, when the height of the tower was revealed as 828 metres, and the name of the tower was changed from the Burj Dubai to the Burj Khalifa, I think to honour the Shah of Abu Dhabi, who helped finance this through the difficult financial periods 2008 to 2010. The second project that is a fairly favourable one is again in Dubai, and this is the Dubai Creek Tower, and this again is the architect's concept. It actually is a landmark tower within a whole large development of tall towers. Many of these towers are 300 metres or so, 1,000 feet or more. But this one, the height has not been revealed, but it will be significantly in excess of a kilometre, more likely around 1.3 kilometres, I think, is our best guess. The main part is here. The client was Emaar. The structural designer was Calatrava, very well-known European designer. The structural and foundation design was done by Oricon. The foundation contractor was Solitone Bashi, and the foundation testing was done by Fugro. And our role here was to act as a specialist consultant to Oricon, who was the foundation and structure designer. The main challenges here was, again, now another world's tallest tower. Fast-track construction had been planned because this was hoped to be a centerpiece of a Dubai 2020 Expo, which unfortunately due to COVID and so on did not actually occur. But again, there were potential problems with foundation capacity in carbonate soils and rocks and extremely large lateral and vertical loads. The challenges were met in this way: intensive ground investigation yet again, high quality in situ and laboratory testing, high level foundation design analyses, but again, also some preliminary analyses, but the final analyses were done using three-dimensional finite elements. There were design workshops, and then there was a load testing program. And here the Osterberg cell was used on barrettes. I think you call them load-bearing elements here, but the foundation system itself was a system of barrettes. And I apologise for the somewhat hazy nature of this, but this was the foundation system. That the main tower was founded on 145 barrettes, and they were about 72 metres long, so around about 250 feet. And then the cables, the cable anchorages were on two sort of arcs here, each of which had 144 of these barrettes, so a very substantial foundation system. And so here are some pictures. This is a typical barrette, the reinforcement for it. That's the installation of barrettes. And here then is an aerial shot of the foundation system being constructed within the main tower precinct. Now, and it's a shame George Osterberg isn't here to enjoy this. A new world record was set during the testing of one of these barrettes because 360 meganewtons, which is in excess of 80,000 kips, were put onto a single barrette via an O cell. And I just mention here that 20 years earlier or so, 60 meganewtons, or 1/6 of that, was as much as we could have on the Burj Khalifa. So that was really quite an achievement. And again, the performance of those barrettes was in excess of the design expectations. So those two projects that I've mentioned, the positive elements are each of them had detailed ground investigation, including geophysics. They used advanced design methods. There was a cooperative peer review process, detailed load testing, and subsequent settlement monitoring. Now, finally, not such a good story. And I think I need to be very careful when I talk about this because I'm just basing my comments on what is publicly available information. But this is a very well publicised and unfortunate case history of the Millennium Tower in San Francisco, the tallest residential tower in that city. It's founded on 945 reinforced concrete piles that are founded in a dense sand layer, but that do not extend to rock. There is, I understand, a clay layer of significant depth below the founding level of those piles. And in addition, to complicate the situation, there's been construction activity in the vicinity, and the maximum settlement has been quite substantial, and the maximum differential settlement has also been very substantial here, far in excess of what was anticipated. So the remedial plan was to install something like 52 additional piles on the high side to try and fortify the foundation system on the high side. And unfortunately, here is an example of one of the issues that I raised earlier in my talk, that when you try and do operations of this nature on a highly stressed bit of ground, you cause significant movements, and they can in fact have a deleterious effect on the existing foundation system. And so when they put the first few of these piles in, there was an additional 25 millimetres of settlement, an inch or so of settlement on the high side. And so work had to stop in September last year. It was resumed cautiously in December. I think now the number of piles that they are going to or have installed is 18 rather than 52. But I gather that the tilt has increased recently after excavation for the foundation extension. So here is a case where a number of good things didn't happen. The foundation system was founded on a dense sand layer that was unfortunately underlain by clay, which had the potential to cause additional settlements, and they appear to have occurred. There has been also, in addition, which has exacerbated the problem, there's been construction activities, both excavation and also dewatering, which may have had some influence on the settlement. But particularly, I think, the remedial measures, rather than assisting the foundation, have in fact created a further problem. And perhaps in retrospect, had more thought been given to this, there might have been perhaps a suggestion that there would be scope for trying to get the high side to settle a bit more, and even the settlements out that way, by using soft methods of correction of the settlements, for example, excavation of the soil or even the RSS method. And that may perhaps have been beneficial in terms of at least initially reducing the tilt of that building. So let me then just make some concluding remarks. I think that to meet the challenges of tall building foundation design, we're seeing that modern methods are being employed for in situ testing, laboratory testing, analysis and design methods, and load testing. And in particular, I think George Osterberg's development of the Osterberg cell test really gives us piles, pretty common that we could never really fully develop the end bearing because we couldn't get enough load into the system to do that. Now with the Osterberg cell method, we can. Simpler methods, however, are always essential to check on advanced numerical analyses because the more complex the analysis is, the more possibility there is that something can go wrong or that there's been an unwitting acceptance of some inherent parameters in the program. I think cooperation between geotechnical and structural designers is essential, and we need to be aware of risks and possible sources of problems, both with respect to investigations, design, and construction. And I think then clearly what we need to do once we become aware of those risks is to take appropriate risk reduction measures to address those problems. And I hope that I've tried to outline in this talk some of those risk reduction measures. Thank you.
I was just wondering what the typical diameter is of an RSS boring.
Look, I'll be honest with you, we haven't actually used it in anger. We did have a design for a building in Hong Kong that was eventually corrected by more conventional under reaming of the soil. But we were looking at holes that were typically 900 millimeters, 1 meter diameter, so fairly large diameter. If you get too small a diameter, it doesn't work because you get arching around the small diameter hole. So it has to be reasonably large so that you actually do remove significantly some of the soil support. You can also consider having trenches, which may not have to be quite that thick. It has been attempted on a model scale in the laboratory in centrifuge tests. My colleague Charles Ung did a very nice example some years ago where he corrected the tilt of a shallow foundation with this process, and I believe it has actually been used in China, but details of that have not been available in English, unfortunately.
Okay, thank you. One more. Rudy, could you make your way to the microphone, please? Or Matt can get you one.
Good morning. Thank you, Harry. Great presentation. What was the time? What was the time frame for the Burj Khalifa total settlement prediction? How many years?
Oh, the time frame. Look, to be honest with you, we didn't. Most of the time-dependent settlement that you see there was because of the addition of stories on the building. And the construction occurred over a period of, about 18 months, maybe 2 years, something like that. It was relatively rapid. We didn't actually do any long-term time settlement predictions because we figured that, this was essentially soft rock, so that most of the settlement would occur as the load came on, and that seemed to happen. And there might be some long-term creep, but we didn't actually try and predict in detail what the creep settlement versus time characteristic would be. But unfortunately, monitoring, I haven't had the most recent monitoring data, but I believe it's still less than 50 millimeters.
Okay, thank you. Any others? I think that's it, Dr. Poulos. Thanks for your Osterberg lecture. And Teresa, are you going to announce the break? Or?
Thank you very much.
No? I'll go right now.